All right, in this next one, we're given another reaction, and we're going to have to do another QC calculation to determine if we're at equilibrium, and if we're not at equilibrium, whether we're going to shift to the right or to the left to achieve equilibrium. So for this particular one, I'll write the reaction again. 2HI is in equilibrium with H2 plus I2. And QC form here, the form again is the same as it is for equilibrium. We're just using different types of concentrations. H2, again, I use this notation to put a T here. This is at just some time. It's not the initial time. It's not necessarily the equilibrium time. It's just some time that I've checked it. I've taken it into the lab and checked the concentration. Okay, and now we're going to put them in the same way. Okay, and this ends up as 1.75 times 10 to the minus 3 times 1.75 times 10 to the minus 3 divided by 1.75 times 10 to the minus 3 squared. So my QC here has a real simple form. It's exactly 1. Again, I like to use a number line to figure out which way we need to shift. It's a good mnemonic to do that. So we go from 0 concentration up to infinite concentration. Let's go ahead and put our Kc on there. It's 2.0 times 10 to the minus 2. We have to decide which side of this 1 belongs on. So it's over here. Qc equals 1. And again, your calculator can do this work if you get confused with those at all. So 2 times 10 to the minus 2. And if it is in this floating notation, it'll give you just a regular number, 0.02. Okay, and so 0.02 is to the left of QC. So the reaction now is going to have to shift to the left. So from QC, concentration is going to have to shift to the left. So we're going to use up product and reform reactant in order to get to equilibrium. Okay, so QC is larger than KC, so it's either A or B. The reaction will proceed from the right to the left, so it is B would be the correct answer there.